Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you all for sticking with this. It's heartwarming. So here's a list of topics from the first lecture that we haven't finished yet. The dark ones are darkest are for today, and possibly some more if you want later. So since it's been a while, let me remind you that we're exploring a proposal for a grand unification of symbolic and neural computation. And the proposal is that there's a very explicit formal sense in which symbolic computation is a kind of virtual machine that runs a neural network microstructure. Mediating between the two levels of micro and macrostructure here, I've proposed that we have a level of tensors. The tensorial level is one of the main innovations here. So why tensors? I'm going to refresh the discussion that we had last time about this, review a little bit before moving on. So why tensors? Well, the answer lies in distributed representations. And why the importance of distributed representations? Well, the reason that we need a unification is that there's a contrast in the syntactic and the semantic aspects of symbolic computation compared to neural computation. And as far as the semantic contrast goes, and I mean the semantics of the formalism, not natural language semantics, but as far as that goes, on the macro side, we have concepts locally encoded in individual symbols. It enables programming because we can connect the individual symbols to the conceptual representations that we have in mind for the computation that we want to program. And we can then write rules to tell the symbols how to behave. But at the micro level, concepts are activation patterns. They're vectors where the activity of a single unit typically has no conceptual interpretation, although there are occasional exceptions. Each neuron is a small part of the encoding of many concepts, which are all superimposed by vector addition whenever concepts appear simultaneously in combination. And that's what I call subsymbolic representation. So why tensors? Well, the reason tensors are important is because they are very natural for distributed representations, as we will now see. So the argument is based in a very general meta principle, which I introduced last time. If a system is left unchanged or invariant under some group of transformations, then the fundamental laws of the system must be invariant under those transformations, under those symmetries. That's a very general principle, and I illustrated it last time. I'm going to just rerun that illustration better this time, tiny modification. So as a very concrete illustration, if we think about the collection of vertical horizontal rectangles in the plane and ask what the area of a rectangle is, well then, of course, the area is invariant under rotations, including rotations that take x and y and exchange them. And so if somebody proposed that the formula for the area was the x width to the power 103 and the y width to the power 0.98, because maybe they did a data fitting exercise where they measured a bunch of rectangles, and that those were the best values for exponents of wx and wy. In particular, they fared better on the data than 1, 1 does. Despite that, we can be confident that that can't be the right formulation of the area, because from symmetry alone, we know it must be unchanged when we exchange wx and wy. And of course, that is not going to happen unless the exponents of wx and wy are the same. So The relevance of the symmetry meta principle here is that a vector space is invariant under a change of basis or change of coordinates. The general linear group of invertible linear transformations is what effects the change of coordinates or change of basis. And as I said last time, if you have a quasi-linear network, and most networks traditionally have been of this sort, where the activation of a vector, the activation vector of a layer acts on the rest of the network through a weight matrix. So it's the result of multiplying A by a W matrix that determines what influence it has on the rest of the system. When you have that kind of dynamics for your activation, then this is invariant under transformations between local and distributed representations under the general linear group of coordinate system transformations. All you need to do is adjust the outgoing weights from some particular layer to compensate for the change of basis in the activation description itself. So we can choose to redescribe activation vectors as we like by changing the coordinate system and by appropriately adapting the weights that link that layer of units to the rest of the network. We can ensure that our redescription has no effect on the behavior of the system. So the laws of a cognitive architecture, the laws of the network that we're going to be positing for our model of cognition must accommodate arbitrarily distributed representations. The architecture can't be restricted to local representations. Yeah.
So this is true for a single layer network. But once you get that output with this transformation is going to be exactly the same as it was before.
Yes.
So then the rotations that you want to apply to these variables at a higher level, you can't quite match them with the rotations in the. It's not like you can take all of the values of all the nodes in the network and rotate them. Because of these.
You can rotate any or all of them, as long as you change the weights coming out of the rotated layers appropriately. Well, so.
Because this is kind of, you have this clamping. You can rotate this one layer so the outputs are exactly the same. But if those outputs are also rotated, you can't figure out what the weight should be to give you the rotated versions of the nonlinear layer, the nonlinear output.
Right. So, yeah, I'm not arguing that we can change the incoming weights to a layer to effect any change of coordinates we want in the outgoing activities or influence of that. I'm not arguing that.
Layer by layer.
Yes.
But there is this clamping that you have to get the same representation of every layer. And then you can rotate.
The right. So what I mean to say is that at any layer that you look at, it must be that were the network built so that the representation at that level were distributed instead of local, or the other way around, then that would be that would not have consequences on the behavior of the system under appropriate modification of the weights. Right. Yeah.
Yeah, but it's okay, right? The kernel neural net has to distribute replace in all the layers except the upper layer, as we discussed. So this point really is to say that the upper representative has to be distributed all.
No, actually, what I omitted the slide from this review, but I pointed out that
we do have
when it
distributed
comes to,
representation in neural net.
but not of roles, just of fillers.
Oh yeah, okay, that's it.
So the conclusion here is that the architecture that we want must not be one where locality is wired in to the role encodings, which means that we have a local set of units for the fillers of different roles. It must be that we can, the architecture must accommodate a situation where the role vectors are distributed as well as the filler vectors. And I want to talk about two examples today of the benefits or consequences of having distributed representations for the role vectors. Okay, finishing this little bit of recap, tensor notation is invariant under this group of transformations. If we write an equation in tensor notation that describes what we want to happen, say, to a local representation, then that same equation is going to be valid for any proper distributed representation. That means a distributed representation in which all of the basis vectors are linearly independent. The same equation may be approximately valid for improper or compressed distributed representations. That's something that we are trying to understand in current work. But we can say for certain that with proper distributed representations, the same equation is going to be valid. And while local representations are lossless, there's absolutely no loss of information when we encode our information in individual units. What this tells us is that the same thing is true for proper distributed representations. They have no loss of information either. Improper distributed representations where you have nonlinear independence among the basis vectors, because typically you have too many basis vectors, then in that situation we expect lossy representations that require some extra work to eliminate noise that comes from the crosstalk of basis vectors that are not linearly independent. And that kind of correction is not necessary with proper distributed representations. Lee thought it might be interesting for me to talk about how tensor product representations relate to various alternatives in the literature for encoding symbolic structures. And so if people want to hear about that, then that's one of the topics that could happen.
Because in your NIPS workshop, 2 days workshop, there will be some discussion on that as well. Because I saw other speakers besides you, they are representing some other
Yes.
things. It would be nice to have
Yes.
someone
That's a good suggestion. I should take a look at the specific set of speakers who will be at the NIPS workshop. So this year there is a 2-day workshop at the Neural Information Processing Systems meeting on relations between neural networks and symbolic computation. So it'd be good to bone up on the particular approaches that have been advocated by the other members of that. Yeah, sounds good. Okay, great idea. Okay, so using tensor calculus, we can actually program networks that use distributed representations, and the case we're really interested in is distributed role vectors, just as we can program networks with local representations. And that's another topic for a next and presumably final lecture if there is one, but not today. Today we're going to talk about similarity-based representations, similarity-based generalization that arises from distributed representations. And we'll talk about it as a subsymbolic example and a symbolic example. So let me start with the subsymbolic example. And this has to do with phonology. The other example has to do with argument structure and syntax semantics. So there is a pretty robust finding in psycholinguistics that when people make speech errors, structural information is preserved. And so Gary Dell and colleagues developed a way to induce these kind of speech errors in the lab with a tongue twister task. People have to, they're shown like the sequence of syllables on the screen written in some sort of English orthography, and they're asked to read them slowly and then repeat them quickly, speeded by a metronome. And people move consonants around when that time pressure is applied. And so you might end up with that error shown at the top of the screen there, for example.
So are you saying that the coda consonant normally don't get changed?
In this, no, I didn't mean to imply that.
Oh, no.
This example does have that property. But what is really the generalization is that the errors tend to preserve syllable or word positions. So if H is going to move to the wrong syllable, as it does in this error, and it starts in the onset, then it will end in the onset. And similarly, the n obeys that principle too. But you have movement of codas as well, and the generalization is that a consonant tends to move from the coda to the coda of another syllable. Errors of this sort and others are one of the classic means that cognitive scientists use to try to figure out how mental representations are structured. And so something like this is supposed to give us some evidence that the representation of this string of sounds really does have something like syllable structure in it, the way phonologists, linguists would say. Now, our explanation from the perspective of gradient symbolic computation of this generalization goes like this. Distributed neural activation patterns encode similarity structure. So distributed patterns can be more or less similar to each other. The greater the similarity of an output to the correct target, so the more the similar is the string on the right, which is what was actually produced, to the string on the left, which was the target, the greater the probability of that particular error. And that's explained by our general theory that the information processing is in production of language takes place in a recurrent network in which we have a grammar. And the grammar assigns different harmony values to different outputs, and the network is seeking to construct the highest harmony optimal output. And one of the types of constraints that we have in our grammars, as we heard about in the context of OT syntax, was faithfulness. So you may remember that's the idea that the expression that is produced for some intended interpretation should have elements which are in one-to-one correspondence with the interpretation. And so when we were talking about the "it rains" example, we talked about how the constraint full interpretation requires that every element of the expression be a correspondent with some element of the meaning. In other words, that it contribute to the meaning, which it doesn't. And it violates faithfulness in the case of "it rains." So just to remind you that the idea then is that if we look at the similarity that arises from different types of errors and measure the harmony or the faithfulness, then we will make predictions about which errors are more likely than others. And so the key third step here is that the role of being the onset of the jth syllable is similar to the role of being the onset of the kth syllable. So there is a non-zero degree of similarity between those two, and that means that when H appears in the onset of the wrong syllable, it still has some similarity to the target. And crucially, there's less similarity. The degree of similarity is lower if we compare the onset of syllable J to the coda of syllable K. Even if we compare it to the coda of syllable J, we'll see that the similarity is less. And so the distributed representation of the roles here is done in a kind of recursive fashion where the embedded onset within a syllable has a role vector, which is the tensor product of the vector that encodes the role of being the onset, the inner role, and with the role of being the first syllable in the string, the outer role. So these are one-dimensional tensors, tensors of, what did I call them? Order 1, I think. Just a standard vector, and the tensor product here gives us a tensor of order 2, which is like a matrix. So it's the in order to, and the way we do the simulations, which I'll show you some results from in a minute, the way we do the simulations is we actually generate random distributed patterns for these vectors, but we constrain the random generation to have the similarity structure that we want. And so we specify some value, I think it was maybe 0.4 in the examples I'll show you, for how similar the role of being the onset should be to the role of being the coda. So the randomly generated vectors here are constrained so that their dot product is equal to 0.4, whatever the value was in that simulation. And similarly, the other vectors, the other roles for which syllable you're in, have a certain degree of specified degree of similarity. That's S sub sigma. And we make the assumption that the similarity of being in the second syllable compared to the first is actually greater than the similarity of being in the coda as opposed to the onset. Now that's a stipulation of the model. We have some kind of story to explain why that makes sense, but we don't actually have a learning story that would produce that as a result. But if you accept that the similarity structure is part of what the model lays down, and this is what we lay down, that the similarity is greater between syllables than between positions within a syllable, then the rest follows. Namely that an output error that preserves the onset position is more similar to the target than one that doesn't, that moves something from the onset to the coda. And so the algebra is simple enough. The target role is, let's say, being in the onset of syllable 1. Let's say this, we're talking about a consonant that's supposed to appear at the beginning of the first syllable. So there's its target role, the tensor product of the onset role with the syllable 1 role. And the error in the role at which it actually appears on the surface in a mispronunciation might be, let's say, the onset of syllable 2. And what we need to know is what is the similarity between the target and the error. And so we take the dot product of these two tensors. The dot product of two tensors is equal to the product of their dot products. So this is equal to the dot product of the first components in the product, that's here, and times the dot product of the second components there. And the I didn't mention it, I should have, that the vectors that we generate have length 1. So the dot product of the onset vector with itself is 1. The dot product of being in syllable 1 versus syllable 2 is, by stipulation of the model, S sub sigma. So that's how similar an error is to its target when you start in the onset and end in the onset. And if we compare that to the same calculation, which I'm not going to go through, to if you start in the onset of syllable 1 but you go into the coda, even of syllable 1, the same syllable, then when you crank through the same calculation, what you get is the similarity between the position, onset, and coda as the result. And the model asserts that that is a lower degree of similarity than this. So
how can you show that using local representation, something like that will never happen? Is there any insight? I mean, just intuition.
So there's no similarity between local representations. And so you have to, you can't get this effect from similarity. You can try to get it other ways, but you can't get it directly the way you can in distributed representations.
Do the authors of that paper subscribe to your explanation here, or do they have alternate explanation of that phenomenon?
That's a good question. So Gary Dell, the first author of that paper, is famous for proposing local representations in neural network form for language production models. So my guess is that, and I'd have to go back and check, that the explanation that they have to use involves manually putting in connections that cause activity to pass from the onset of syllable 1 to the onset of syllable 2. So it's built in a certain way. I would say so, but you know, we are also building something in here. Okay, so given that the error in which the onset position of the target is preserved in the output is more similar to one where we go from the onset to the coda, then it follows that it should be more probable because of the general relation we have between harmony and probability. Higher harmony translates to higher probability. So I'll show you some dynamics of the some results of our dynamic network. In a few days ago, my Wonder postdoc produced these beautiful actual correct simulations, pictures of simulations of our network crawling up drunkenly the hill as quantization is increased and the bumps at the discrete points get steeper and steeper. I showed you a mock-up of that, but this, I think, is the real thing. So that's let's see. Do I have another one here? Yes. So this is a slightly different version, in any event, just to remind you what the dynamics was of the network, without having to go through any of the formal respecification of it. If we run our dynamics of this sort to produce pronunciations of these CVC syllable strings, then what we find is shown in this graph here. First of all, we're talking about just 2 syllables now, not 4. And the consonants are just named 1, 2, 3, 4. 1 is in the onset position of the first syllable, etc. And so here are a bunch of errors that the network might make. There's the correct answer, which is exactly the same as the input. And then here are a bunch of things which are errors of different sorts. And we can compute the harmony of them, which is, in this case, just the degree of similarity between the error form and the target, which is the calculation we just went through a moment ago. And it looks like this, because these are the errors in which position is preserved. So what should be in the coda of position of the second syllable appears erroneously in the coda of the first syllable, as well as appearing in the right place. These are ones where the syllable is preserved, and that gives less degree of similarity, so the harmony drops, but it's still more similarity than if you go from the onset of one syllable to the coda of a different syllable. Nothing is preserved, neither position or syllable. But that's better than errors in which you have 2 mistakes, and these are the best errors with 2 mistakes because they're the ones that preserve position in the syllable. So that's what this stair step is plotting, is the gradual decline in similarity between the error form and the target form. And if we plot the results of the simulations, not as beautiful as I would like, and we need to understand better the discrepancies, but what you see is that there's a monotonic relationship between what we predict, what we expect, and what we see, but it's not perfect. And in more recent simulations with much greater numbers of repetitions and so on, we still see discrepancies that we're trying to understand. But at least we can say that given this error pattern from the network, we can understand why these are intermediate in probability between these, and so on. So I should say that this relationship, which I was saying we're trying to understand, is the relationship between the harmony of an output and the probability that the network actually ends up at that representation on its random walk over the harmony landscape. And I'll just remind you that we had a theorem to the effect that the probability that the network state ends up very close to some particular discrete output, one of the error outputs on the horizontal axis of the graph, for example. The probability is proportional to the exponential of the harmony in the grammar of that particular discrete output. So we're trying to predict how probable a particular output is based on its harmony. And this theorem says that that should, in the appropriate limits at least, work for us. But we're still trying to understand the discrepancy between the limiting prediction there of the theory and what we observe in practice. Okay, yeah, so, sorry. This is just to say that the probability is what we're seeing here, and the harmony is what we're seeing here. Okay, so that's the end of the little spiel about how if we have distributed representations for roles, namely positions in a string of speech sounds, then we get leverage on a very robust finding, which is that errors tend to preserve positions in some symbolic structural sense. Okay? Okay, well then I'll turn to my second example, which takes a lot longer. Rather than being at the subsymbolic level, this is at the vector symbolic level. So we will be talking about tensor product representations exclusively, not neural net simulations using them, non-dynamical observations actually. So the domain here is verb argument structure. The role vectors involved in linking the syntactic roles of arguments in a sentence to the semantic roles that they bear in their interpretation. The similarity arises from distributed representations, and the role vectors are going to be constructed from tensor product representation procedures. And what I want to show is that there's it's possible to define a single distributed vector that generates the correct semantic roles when combined with either the syntactic roles of either a transitive clause or an intransitive clause. And that is an interesting result because there are differences among verbs in how their transitive and their intransitive forms relate to each other. Different verbs impose different mappings from the syntactic to semantic roles. But there is a high degree of similarity among the mappings across the set of verbs. So there are what are usually considered to be classes of verbs, but we can have a more refined articulation, I think, following this line than that. So what does that mean to have different argument structures? Well, in a very typical case, what we have is the following kind of alternation. Actually, I'm not sure why I started with this one. This is maybe the less typical case, but more interesting. So in a transitive clause, the verb spin has an interpretation for the subject of the sentence, J, as the causer. So J spun K around the room means that J was causing K to spin around the room. In the intransitive, you get actually the what's called the anti-causative form. John spun around the room means John was the affected party spinning around the room. So the subject in the transitive case maps onto the causer, but in the intransitive case, the subject maps onto the affected party or the theme. So in order to formalize this, we need some characterization of grammatical functions, and something that's extremely convenient for us comes from what's called typological functional syntax, where there's actually a distinction made between the syntactic roles in transitive clauses and intransitive clauses.
In that case, I just simply use one single feature to distinguish span, the first one and the second one. Right? It has the same meaning, but one is called in the subject form, the other is. I don't know what's the right terminology. No, it's not going to explain that. To me, I just list that into two different words. They just happen to be spelled the same as smell.
No.
You want
No,
to do
because they're related.
that?
Right. So
It's not like I said,
Yeah, okay.
John spins around the room and the cake bakes. They're not separate.
Oh, yeah,
They're in the same space.
Okay.
You can't say that.
but I think what I propose might not be too far from what the kind of thing you were thinking. You'll tell me if that's so. The syntactic roles that Dixon uses for subject and object in a transitive clause are A and O. Now, you can use a mnemonic that A is like agent, but that's potentially misleading because this is supposed to be a syntactic role, not a semantic role. Okay, so A is the subject of a transitive clause and O is the object of a transitive clause. In an intransitive clause, the one and only argument is called S. It's the subject of an intransitive. So those are the three syntactic roles that we're going to be using. As far as semantics roles are concerned, we'll just use theta roles, and I want to treat them in the way that Dowdy proposed to think about them as kind of prototype bundles of semantic features. So the agent semantic role bundles together being the causer. So your prototypical agent is a causer, is volitional, is animate. Your prototypical patient is affected, non-volitional, inanimate. And the argument structure types are the mappings between the syntactic roles and the semantic roles that different verbs deploy. So one of the argument structures is the causative transitive, which we saw already, where the subject of the transitive clause is semantically mapped to the agent role, and the object is mapped to the patient role. That's your canonical configuration. And then in the intransitive anti-causative case, which was J spun, the S is mapped to the patient role, like the object would be in a transitive sentence, even though it's the subject of the verb. Okay, so yes. So this last pair is what the verb spin deploys. So because it has a transitive and an intransitive form, that one verb carries with it these two argument structures. And now for the vector encoding, we're going to be using some basis vectors from a semantic space and a syntactic space. And I'm going to assume that these basis vectors are orthonormal to each other. And I'm going to interpret them. I'm going to assume that they've been selected to be meaningful. So these, if at the neural level we have a distributed representation for masculine, then this is the basis vector which gives us that direction, the direction of the distributed pattern. And so if we use it as our descriptor, then we have localized the masculine feature to that direction in semantic space. So J has associated, the vector for J is the sum of a bunch of basis vectors that spell out the properties that J has, the referent has. K is feminine and has other properties. So those are in semantic space and syntactic space. We have these three vectors, orthonormal. And down at the semantic role level, the agent vector is the sum of the vectors that point in the direction of the prototypical properties, causer, volitional, and so on. Patient, same story. And now I'm going to write down a tensor for the causative transitive argument structure. And what it says is that the agent role is paired with the subject of a transitive clause syntactic role. So this semantic role is paired with this syntactic role. This semantic role is paired with that syntactic role. And this whole thing I'm calling AO. It's the AO form for the syntax. So Y is going to be representing syntax because S is already used for something else. So revert to the second letter of syntax. And the type of tensor we're talking about now is a second order tensor. Each of these are first order or vectors. And the second argument structure associated with this verb is one in which the patient is mapped to the syntactic role of being the subject of an intransitive verb. So this is, I'm calling OS as the, it's the mapping in which the role S behaves like the role O in being mapped to the patient thematic role. And since spin has both of these associated with it, we add together these two tensors to get the total syntactic characterization of the argument structure of spun. The full vector encoding of the syntax semantics for spun is the tensor product of this vector, which characterizes its syntax, and this vector, which characterizes its semantics. And the semantic vector includes things like spin has rotational lexical semantics, it has past tense, and so those are properties of the meaning that are bundled together here.
Yes, so why is that tensor encoding for a word is defined to be the tensor product of two syntactic and semantic? How do you justify that definition?
Well, what it is, well, as opposed to what one might ask, why am I not adding them together? Why am I multiplying them together? The fact is that we need to stick together the properties of the semantics and the property of the syntax, and the tensor product does that. So you'll see how that fact is plays out when we use this verb, this encoding of the verb, to derive the semantic interpretation of full clauses.
So what's Chomsky's syntactic theory to say about this? There are not many English words that behave like this. There are not many English words that behave like
Quite
this.
a lot. Quite a lot. And
There are other languages where, for
That's the
example,
normal.
Japanese, where these are
They have that.
lexically encoded as
Okay.
So if you want to
separate
see
forms.
examples of these, I have a book called Verb Alternations by Beth
Really?
Levin.
Mhm.
Oh, really?
And,
Yeah.
and it has all of these various alternations. This is just one of them. If you have the garden swarmed with bees, bees swarmed in the garden. There's a whole set of those. It's not rare.
I see. It's just,
But they are
we're just
lexical.
unconscious about it.
Yes,
And the cool
that's how
thing
it's
is-
supposed to be.
Yeah.
The cool thing is that you can induce a new, you can kind of force a new, that type of a meaning onto a verb that doesn't really belong into the class
I see.
by using it in that canonical way. That's how Hobbes or what Calvin always could verb any noun, right? It's that principle. And I think this is nicely explained by this.
Well, let's see what you can do with this. I just want to point out that the overall tensor for the verb ends up being third order because semantics adds one dimension and the syntax already had two. Okay, so let's see. I wanted to give another example here. Oh, this is the case. This is an alternative case. So in the case of J stirred cocoa, in the transitive clause, J is the agent. In the intransitive form, J stirred endlessly, J is also the agent. So this is the perhaps more obvious situation of a verb in which the subject always gets mapped to the agent, irrespective of whether the clause is transitive or intransitive. And so
where it's
yes,
so you have both of
right.
those.
Having drunk too much caffeine, J stirred all night.
That to me is a same word of different meanings.
It has two different interpretations of the subject,
Okay.
and
Okay.
Well, it would be interesting direction for us to pursue to think about how to incorporate that that degree of variation, whether you call it polysemy or not. Yes, I wonder how this analysis would fare, trying to get both John stirred. Yeah. So.
When you have something like J spun or John stirred, is it context dependent how you interpret it? Seems like it could be interpreted different roles based on the context.
Yes, well,
Because you had to say, having had too much coffee.
right.
Right. So
Right.
if
Well,
you said-
I got the intended interpretation without that, but I thought it would be that much more obvious for people with it, right?
But
Um,
there is a question is when it's in context, so Jay stirred endlessly the cocoa.
Needs to
If
be
it's
mentioned
understood,
earlier. in
is,
this
if it's
also.
been mentioned earlier, is it there or not?
Yes.
When we analyze this, those are deeply philosophical questions, but maybe not philosophical, but they end up really
Well, it sounds like
hard to understand.
you're saying that J-spun is an unambiguous role for J.
I'm treating it that way, yes. Yes, that's
But
right.
in real English, it's probably ambiguous.
No,
No,
because-
but
no, because
Jay
even-
can spin.
And Jay can
Yeah.
spin soup.
It can be
You
spun.
actually have that, you actually have, for the same thing, Jay spun endlessly. Jay is somebody spinning silk.
Right,
off
Jay got on
the
his bike,
wall.
Jay spun.
Right. But
Or-
here,
Mhm, mhm.
there are other, in J-spun, there are other analyses where J spins J, where J is the understood object,
Right.
so.
Both the causer and
both
the
the causer
effector.
and the effected.
Right.
John spun himself. So it
Right,
just
right.
depends on how many understood arguments are you going to analyze or not.
So, what Lucy's bringing out very cogently is that there is an assumption in this analysis of that makes it a very surface-oriented or superficial analysis, in the sense that the assumption is that if you don't see an object in the sentence, then there isn't one, as opposed to analyses that would suggest that there's an invisible object in the clause. It could be an invisible reflexive pronoun, like John spun himself, right? Or it could be John spun the cocoa. But I'm treating these at face value without positing any hidden arguments. But that's almost certainly the wrong thing to do in the bigger picture.
In terms of harmony theory, then would harmony have to somehow model the context as part of the best fit?
Yes. Yes, you try to use the interpretive process as one where you're cumulatively building up a representation of the discourse, and so certain interpretation of the current sentence would be more harmonious when added to the state of the discourse than others might be. Okay, so getting back to the slide here, we talked about the anticausative intransitive with the example of spun, J spun up here, and then this is the causative intransitive, J stirred, and that pairs the agent role with the S syntactic role as opposed to the patient one. So this is AS. The S is treated like the A role in the transitive. And so the syntactic structure for stir is going to involve adding this one with this one, AO and AS. All right, so now comes a very big table, which I'm going to incrementally expose, but I'm warning you, it's a big table. Okay, so there are many cases that we want our proposal to account for. So just to, the proposal is that a verb is encoded in this way. And I will make a proposal about how sentences are represented in the next slide. So J spun K. Those are the syntactic roles we talked about before. J is in the A role, K is in the O role, and the verb role is spun. And here's how I propose to vector encode this, that J is bound to the role of spun in the agent, bound in the role of the A of spun. The subject role of spun is what J fills. So this is filler times role. Filler times role, K in the O position for spun. And then the semantic interpretation process is going to correspond to a contraction of this tensor. So the verb was up at third order. The A, which is the role within spun, is a fourth order, and J is the fifth order. And by contracting over the last two indices of these five, the third index of spun and the only index of A, by contracting over those two, we get an inner product which reduces this down to what we need for semantic interpretation.
So earlier slide, you showed that each word spun can be shown to be the tensor product of two semantic and syntactic. So how do you put the sentence together? What rule, what's the assumption made about composing this whole sentence? I mean, just want to understand the vector encoding that equation. How do I make sense of it?
Well, it's the straightforward case where you have a set of roles for the sentence, and into each role you're sticking a filler. The roles for the sentence are determined by the verb. So the verb, since it's a transitive clause that we're representing here, the verb brings with it an A role and an O role.
Okay. So what do you have at here between J and K term?
Sorry, why do I have A?
I mean, you have two summation, right? There are two terms. One is J, A.
Yeah, there are two filler role pairs in this clause. J is one of the fillers, K is the other filler. Each one fills a role that it's bound to with the tensor product. And as is typical, the different role filler bindings are added together.
Okay. And that can be read directly from syntactic role, or do you have additional assumption to write down that semantic representation?
I think what you have to say is that the tensor product decomposition into fillers and roles is the one that deploys the roles that come with the verb. So we are bundling together this and this for the second role, and this for the first role. And that's just to say that being the subject of a verb is a relationship in which we have the syntactic properties of the verb being bound to this.
So can that be interpreted to be a tree, and then you use the positional role to create equivalence of this vector encoding, or is it beyond that? Earlier one, you have the semantic tree, like AMR one, you have the tree or graph. So that's an alternative encoding for the semantic tree, or is it?
Yeah, I think, or the Neo-Davidsonian approach that we talked about
That
is
would be
different
nice.
from this.
It's
It's
different
different
from
from
this,
this
okay.
because we have
I see.
a number of
I see.
bindings to an event variable.
Okay.
So-
So AMR,
Mhm.
that kind of coding, is separate, completely separate, or is it any connection between that encoded and this encoded? The AMR has the tree, right, or the graph.
Right.
And then if I do, define whatever position in MMR tree or graph,
Right.
eventually does it get to the same encoding process?
It's different, although I don't know whether a difference that makes a big difference or not. But in the AMR world, it's partly like the Neo-Davidsonian approach, in which
I see.
we say that J is an A0
Okay.
of some node,
Yeah, I got A0.
and
That's the
that
role,
same
right?
node is an instance of spin.
Okay.
So we have spin and J both attached to the same node, but not attached to each other,
And this
the way they
one-
are here.
Okay.
So this involves higher order combinations than the AMR approach does, but the AMR approach introduces all of these extra variables for the nodes, like the Neo-Davidsonian event variables.
So maybe AMR can be all switched into this representation that make things much
Well, I don't know if it would make things easier, but that's the right question to ask. I don't know the answer. All right, so yeah, oh, I already said that. Those are the 5 indices of the 5 dimensions of this overall tensor for J filling the role of A of spun. Okay, and so now when we expand out the definitions of J and spun, we'll end up getting terms like what we see here, lots of terms like this. So what you will end up getting after we do the contraction with the semantic interpretation, we will get 3-way products, because we start with 5 orders and then we do a single contraction, which always reduces the order by 2 by setting 2 of the indices equal to each other and summing across that dimension. So we go down to 3, and what we end up with is from the J vector we get a masculine feature. From the spun semantics we get rotation feature. From the spun syntax we get that this is a causative, is a causer in the event. And so that's what gets translated in symbolic terms, something like this. We have some masculine guy X who's causing rotation, and some feminine guy Y who is affected by rotation. That's the symbolic interpretation. And here's all of the things that need to be explained in this very first pass. This is very, very simplified, of course, but it's still already, we've got the spun case, the stir case, which is different, and then we have another case which is different again. And as Lucy suggested, there we could have probably easily 30 types instead of 3 on this slide. So what that slide showed, to break it down, is we have symbolic semantics indicated here for the different expressions, like J spun K, J stirred cocoa, J spun, the intransitive one, J stirred, intransitive one, J felt metal, J felt. I'm assuming that J felt is actually not well-formed English. Unlike the others, it doesn't have an intransitive form. So it's got 0 down here for the semantics associated with that. Those are the symbolic semantics that we're trying to derive, trying to explain. Through the vector semantic representation that I just laid out for the case of J spun K, here's what it looks like for the other examples. And nothing for the intransitive form feel. The symbolic syntax is the binding to syntactic roles of the different arguments. And the vector syntax that comes along with it is what we just saw. So just to spell out what we have in the other cases, besides the J spun K case, we have J spun, the S role now because it's intransitive. And so that's the representation of the sentence in the vector form. And similarly, here we have a transitive and an intransitive counterpart. So syntactically, the spun case and the stirred case are the same. It's when they get mapped into semantics that things change. So that's those are the sets of cases that will work out properly. Semantic interpretation is always just going to be contraction over indices 4 and 5. And that's what's going to take us from here down to, well, from here to here, which is then straightforwardly interpretable that way. So now this slide is to show how the math takes us from this proposal, and this is where you'll see the work that's being done by having a 3-way tensor product here instead of saying adding some of those together. See how the math goes from that to this. Okay, so looking at the transitive case first. I don't know why I did that twice. Okay, so this vector here has a bunch of basis vectors associated with different features, including masculine as its definition. So that's going to end up down here through the following process. And spun is got the semantic part, including rotation, and the syntactic part, which is its two different argument structure configurations for transitive and intransitive. And through contraction, we're going to end up with this guy down here. You'll see that. So this syntactic semantic mapping for the intransitive situation involves pairing the patient role with the subject of the intransitive, the S role. Now, when we do the contraction with this, which says that actually what we're talking about now is the A role, not the S role, because it's the subject of a transitive, not an intransitive. When we do the contraction with this role identifier here, A, then here's the contraction. Those are the fourth and fifth vectors that get, we take the dot product when we do the contraction. The dot product of ES and EA is 0. All the basis vectors for the syntactic roles are orthogonal to each other. So that causes this whole thing to be wiped out, and that's why we don't end up assigning the patient role to the subject, which we would do if it were the intransitive form. So that knocks off, essentially, there's no contribution in the end from that syntactic role there. It's the other one that's going to end up doing the work. And that's the one that says that when we have a transitive clause, we bind the agent to the subject position and patient to the object position. We take the dot product again with the role that we're actually occupying, which is the A role. And that wipes out the second part because that pertains to the O role. So that goes away. But the first one remains. The dot product of EA with EA is 1. And so that leaves us with the one semantic property agent left. It has not been wiped out. It's the appropriate one. So we're doing a kind of, we're pulling out from all the different possibilities that are buried in here, pulling out the one possibility that is actually the actuality here for the particular argument we're looking at. That agent thematic role vector was defined as a sum of different prototypical properties. And so all of those end up in the final result. And I've just copied one of them here. The others are all there too. And that's it. I think we're done. So all the information packed into these vectors now has been unpacked through that contraction to pull out just the relevant combinations for, in this case, for J, the subject, and here one of the factors that come out with K.
Yeah, so this is not related to unbinding, or is it? So you extract the role vector out of the original full representation.
It is. It really is unbinding. It is really unbinding. We're asking essentially of all the information in here, let's pull out the stuff that pertains to the A role. And that's what the dot products of 0 are doing. It's knocking out the other things. Just like when we unbind, we knock out all of the roles that we're not trying to unbind and pull out. Yes, they have to be orthogonal if we're going to use this way of doing it. So
mapping that to the logical form at the end.
From here to here?
That's just one-to-one corresponding to each other?
I'd like to think so.
People do logical reasoning based on the last line.
That's right.
So now your argument is that when you do reasoning from one to another, you actually all the logical rules can be done simply equivalently in that semantic space.
On here. Yeah.
That can be proved. That would be very useful. Let me throw away logic, just do everything in your own.
Well, that would be cool.
Nobody has done that. So you said A, this to B or whatever, So
there have been
logical rules.
There have been models that do logical inference, but I don't know if there's been an actual theoretical.
But how do you convince us that that semantic representation, the second line, is one-to-one corresponding to logical statement there? It's not obvious. When I look at this, I can see the correspondence.
Yeah, I'm not sure that. I'm not sure exactly what form this ought to take, really. So the failure of one-to-one correspondence here that I see is that these are bound, these are put together, and this is kept separate. I don't know whether that's really the right thing to try to accomplish here, as opposed to just saying that X has the property masculine, X has the property of being a cause, or X has the property of being part of a rotation event or something like that. Yes?
Which takes me to my question.
Yes.
Really back to sort of generative semantics in the early 1970s. How does this contraction work to capture the similarity between he sank the boat and he caused the boat to sink, or he killed the guy and he caused the guy to die?
I think that
If we pull that out, the causation out, and do the tensor math, are we going to get something very close to the same?
I think so. We would get something very close to the same thing. Yep. Yep. So whether you actually use the lexical item cause, you know, if you say John caused him to die, then using the lexical item cause is one way of getting this in, but we can get it in without the lexical item as well. But I suspect that there would be a convergence from the two starting points.
Did you decode them to compare the similarity, or could you compare similarity to the top line code form?
Here?
Yeah.
Yeah, oh, if you took
You're
the
going
dot
to get
product, you should get
concatenated
something
there.
very large of these. Take the dot product of these, you should get something large.
Similarly, you have J spun K, K spun, and K was spun. How does it interact with the passive?
Well, to the superficial level to which things have been taken, I would think the passive would come out the same as the active.
Because you've used in your examples, J spun K and then J spun, but if you had set up the example to be J spun K, K spun,
Yeah.
K was spun, K spun.
Well, there is the question of whether we can put the right argument structure information into the passive auxiliary so that it will bring out that its subject is caused and not causer. I don't see a reason why that shouldn't be doable.
Right, should be doable.
Right, as long as we can avail ourselves of the cheat to say that this is the passive auxiliary was and not some other form of was. Okay, so let's see here. So here's what we can say about these verbs, distributed representations. I think I want one more here. I showed these, a couple of these on 2 slides ago, but this is a more complete characterization of a set of verbs here. What you see is that there's this one class of verbs that all have this argument structure, as opposed to, this argument structure, as opposed to this one. This is the stir versus spin contrast. So there's a certain similarity among these vectors that is contributed by having a similar syntax. Then there's an orthogonal dimension of similarity that's involved. These are similar in terms of involving rotation. This is different. It involves translation. This is similar to these involving rotation, but it's different on the syntactic side because it's an AS and not an OS verb. It's intransitive, is a causer and not an affected party. So anyway, and then there are entirely different kinds of theta roles that need to be incorporated for increasing the vocabulary, so you have experiencers and not just causers and affected parties and so on. So that would be yet another dimension of difference on the syntactic side, even though there might be some similarity on the semantic side. So what I want to just show in the next slide is a vector picture that partly shows the different dimensions of similarity in this space of verbs here, but emphasize that it's really not just a number that says how similar is this verb to that one, 0.7, that we really care about. We care about a much more multidimensional set of similarity relationships than that.
So how do you think this is actually done in Brain, how this computation? Because the mistakes we make in misunderstanding the text indicate that we don't have the full tensor in mind when we do this multiplication. It isn't just a multiplicative error. It would be that I read this and I just forgot about a particular part of the syntactic tensor. So my tensor that I was using was incomplete, and then upon the next reading, I understand that what I missed and I put it back in, which then indicates that I don't really have this full tensor that I then unbound, but that there is some kind of iterative thinking going on. That this, not everything is exploded into a huge tensor before it's being collapsed.
Well, that's a good question. So one possibility, as you suggest, is that somehow doing the calculation correctly calls for larger tensors than we can actually accommodate. I would not want to go down that road myself, but it is related to the road that we sort of are forced to go down in the application domains where we have many, where we have 15,000 symbols or 30,000 symbols, and we're not going to be able to encode the full tensors that would result if those were all linearly independent, and so we have to throw away dimensions or do contraction or do some kind of projection onto a subspace. So I think all of that tensor reduction is relevant to lots of things. And maybe it's relevant to this. I need to think about that more. But what we're talking about adding to, in extending this in the various ways that we've talked about, doesn't involve increasing the order of the tensor, though. So I think that the fact, it's a pretty modest order tensor, and I don't know that we would really want to say that people can't hold that much in mind, but it certainly is at some cost, and so there might...
Sometimes there is maybe more in the order, but in this case,
right.
In the order, it will be just one part of the tensor, the edited part being lost, just not edited.
One of the summands?
Yeah, one of the summands was just not edited.
Uh-huh.
I don't know why it wasn't edited.
Mm-hmm.
But that's the sort of mistakes that we make when we read.
Uh-huh.
Because if it was all encoded, we wouldn't make a mistake. Or it would be a random mistake based on calculation, not by omission. We make
Right.
omissions.
Right. One thing that's known about vision is that it takes a certain amount of attentional resource to bind information together. And so the formation of these tensors that involve binding information together may involve attentional resources, which could just be missing. At some moment, you just don't have the attention needed to do it. So rather than the capacity not being big enough, except in the very important sense that the capacity for attention is limited, and how that would be implemented, I don't know. But it is true that the process of forming the tensor product representation involves lining up the components that get multiplied together all at once, and coordinating them so that you have the right things being multiplied together at the right time. So there needs to be some real serious control mechanisms involved there, and so that might be exactly where you would expect failures of attention to lead to just falling out.
Also now, for this example, the unbinding is really critical. Otherwise, you cannot derive
Yes.
the semantic representation from syntactic formula there. So in that case, how does that contracting done in real neural network? With the neural brain, it's just firing.
Mhm.
You can think about multiple matrix firing, it's firing. And how is it done? In cognition, the human cognitive system.
Right.
That I'm finding that eventually gives you semantic formula.
What I don't know the answer to that, and I guess what I have started to wonder about, but don't have anything really to report, is what in general this kind of contraction is needed for and used for. So sort of what is this one? What is the general case that this is an instance of where contraction has to be used in order to do something like semantic interpretation? That's a pretty new thing in this line of work. I haven't really seen contraction invoked as kind of a cognitive operation of this sort. And so I really don't know what the general picture is that it should be part of, but that's something that I'm trying to think about.
In terms of just computational efficiency, if you're not doing it in brain, then it seems to me like with adding these syntactic roles, and in other examples you've shown in other talks, that you're managing to get a mixture model by using this additional huge vectors that are orthogonal to each other, so that when you multiply, one part is going to be lost, the other part, so you can do inference. But you could actually just do the inference the way we do it in computers by not having these vectors, by having just discrete pointers to these things.
Mhm.
Use pointers instead of these vectors. Seems like this is an elegant way in neural infrastructure to implement pointers, but maybe if you're doing it in neural network or in computer, you don't have
Right.
to go all the way with tensors with all of these parts. You could actually be doing inference, which is try this, then try that, and so on.
That's the same thing we discussed about symbolic computation can equivalent to the same thing as neural. But I think my personal, well, maybe I'll wait for you.
Well, I heard the point as being somewhat different from that, which is that you could say that if I back up to this, let's see here, the table. Where's the table here? Well, this is good enough. This is good enough that we can imagine a nice fat 5-dimensional set of numbers here. Or we could just sort of write this formula down in the computer's memory, and whenever we need it, we perform whatever multiplications and additions are called for that correspond to doing the contraction and doing the tensor products. But we don't pre-compile all of those operations into one big structure. We do them as needed.
And furthermore, some of the multiplications may not be needed because they're reduced to do this or that. So you can just see which one you should do and not do the full computation. So it seems like there
Right.
could
So
be a lot of
every time we got a
computational
0 there, we basically avoided having to do a
Yes.
bunch of multiplications,
Yes.
which you otherwise would have had to do.
yeah, which is similar to a mixture model or an indexing model of some sort. In generative models.
Mm-hmm. Yes.
So, and then the
That-
question is,
that's a-
does the brain actually do something like that in addition? Because it would be interesting if it's redundant, that it actually does have all these high dimensional representations. It can collapse things by multiplying, but it can also just say, have in memory some stored answer and say, this triggers go there and pick that up instead of doing everything through multiplication.
Well, it is a main research topic in psycholinguistics about how much generative apparatus is pre-compiled and stored as such, and how much is performed, how much generative operation is performed on the fly when it's needed. So I think it's a complicated answer that calls on both of them being involved. But certainly, we have to store the information somewhere that is being multiplied together. So we at least have the redundancy there. That somewhere we have the vector for j stored, so that when we need it, we can haul it out.
There's a recent paper that Steven Pinker says is probably one of the most important to come out of cognitive science in a long time, which suggests that A and O actually have separate locations,
Ah,
close but separate locations in the brain.
right, right.
The author's names escape me right at the moment,
Yeah.
but it's scheduled
Franklin
to talk
is-
about it.
Franklin is the first, is the lead author.
Yeah.
And it's PNAS, I think,
Mhm.
not mistaken. Yes, that certainly is a very striking result. That when you look at brain activity for pairs of sentences in which you only vary one item, minimal pairs of certain sorts, very much like what we were talking about the other day in our meeting, where you look for areas where the passive sentence and the active sentence that is supposed to have the same interpretation don't differ in their encodings, but when you change one of the arguments, it does alter the representation. And you find that the minimal pairs involve changing the agents allow you to extract what the agent is by looking for an activation pattern within one region, and if you want to look for what the patient was, you need to look in an adjacent but different region. Yes. The authors make much of, they portray the situation as, if I'm not mistaken, this is exactly what the computer metaphor in cognitive science led us to expect all along. And I had to grimace when I read that because...
They were talking in terms of pointers, for example, which is why I was reminded.
Yeah, right. They do, but I don't see the justification for talking in terms of pointers really in what they've shown. But in any event, the paper is consistent with a very literal-minded mapping of registers from some digital sentence processor into areas of the cortex. All right, so I think this is maybe my last slide here, just a picture of all of the vectors that we just talked about and how they're laid out in, so this is a similarity table where if we cared about the actual numbers, this is the dot product of the vector for spun and the vector for swirled, the 6. It's the product of the similarities of the semantics and the syntactic part, but I don't think we should necessarily care about that really. What is more important is that there are different parts of the space here that have interpretation. So over here are the verbs with the semantics of translation, and over here are the verbs with the semantics of rotation. So these are similar in that respect and different from this one. Whereas this separates the verbs that have the argument structure in which the object, the intransitive subject behaves like the object of the transitive and being affected. Whereas here we have the verbs that are syntactically like stir in having the subject of the intransitive act like an agent. Anyway, the idea is that by using distributed representations for all of the roles that the verbs lay out in a sentence, a transitive sentence, intransitive sentence, by looking at the vectors for the verbs as distributed patterns that have certain dimensions of similarity among one another, and we are in a position to be able to imagine that acquiring a new verb could be a matter of attaching it to one cluster or another in terms of its syntax, a different cluster in terms of its semantics, and getting automatic generalization to the behavior of verbs in that class as to whether their arguments are behaving one way or another. So I think that this approach has some promise for making good on the idea that we can do similarity-based generalization in abstract regions, such as whether two verbs share the same mapping between syntactic and semantic roles.
Yeah, so this is much more meaningful similarity measure than the word to back, the one we had this morning about that. They want just looking at the context to get back vector out.
Yeah.
And this is a real vector in terms of, so that vector is the summation of this order. No.
Mm-hmm.
Yeah, so try to think about this vector computed from off. Okay, so since you choose the basis randomly for satisfied property, and there's no unique numerical value for the vector we talk about here in this vector space.
Right.
But only the similarity are preserved. So when you use a different random numbers, so the random number for the basis, you have different direction.
You have different.
But it's just a relatively they are similar to each other.
So the idea was that the meaningful dimensions like the A role and the S role and the O role are orthogonal to each other. They could be at the lower level. They could be any kind of distributed patterns, and it wouldn't matter. So the random choices of the don't matter. But what does matter is that they are orthonormal. And if they were not orthonormal, you might be able to redo this accordingly. But this was done under that assumption, and it does matter. So let's see here. Yeah, I think that's finally the slide I was looking for. Sorry. Right. So these are the vectors that I was plotting
Yeah,
here.
exactly.
So they end up being three-dimensional tensor in this example, and then you have to unwrap it into a vector to show, if you were to show it actually the way you did, right? I mean,
Yeah.
they
That's
already-
2 dimensional, 3 dimensional, 2 dimensional.
So three. Well, because syntax said two.
Oh, syntax is 2.
Right. Let's see here. Yeah. That was a mistake.
Okay, syntax is
So
2,
if that's stored in a neural network somewhere, can you actually rotate that and still, don't you have a problem because you have the ordering within the tensor of these things?
Right, so effecting a change, the transformations that correspond to rotations in terms of preserving inner products for the tensors involve operating on the different factors and not on the thing as one collapsed whole.
Right, so that will create a problem if we, for the rotational thing, if we consider that a neural network is storing some kind of set tensor in some order.
Yes, so I consider the choice, this rotation business to be a descriptive matter, not an internal matter. You know, as theorists, we're free to change our description to make it meaningful to us.
But then if you imagine that what happened is that there's all this bounding and you have this tensor, and then you probably have some kind of projection because the neural network is small.
Okay.
Then in the end, you probably have maybe a third, fourth, fifth order multiplication of these components that are the real vectors, the underlying vectors. And so we talked about it actually last time as well. So couldn't we just try to fit it to the data because every word comes with different descriptors, like whether it's an agent or not, whether it's causing or not, and so on. Could it be possible to just go back in, for example, an RNN and look at all these things and just try to solve this nonlinear system in one way or the other? Because this reminds me of Bill Freeman's paper on separating style from content, where he was using simple bilinear models to apply to images to find the differences. So I'm wondering if something like that would make sense here. Like we talked about it last time, that in vocabulary, in a dictionary, you have different descriptions of every word. So if you just look at the embeddings, not embeddings, but as an RNN goes through the text, the state representing every word, see if we can show that at the right moment it actually gets the right masculinity and so on. You can actually have another kind of neural network that's predicting from the state of the neural network whether it's actually masculine or not. The word.
Mm-hmm. Right. That reminds me of a method of functional neuroimaging that was very important and popular early on. I'm not sure it still is, but where you actually sort of you have a time series of states of the network, and in this case it would be processing word 1, processing word 2, and then you regress that with indicator functions, masculine, and pull out the coefficient vectors are the patterns of activation associated with masculine, or whatever the factors that you put into your regression were. That could be, it certainly was revealing. That's a very, very cool idea.
Independent regressions and you get one result, but if we assume that something akin to this is happening,
Yep.
then you actually want to fit the bilinear model.
That's right.
That's or trilinear for model
Mhm.
of a certain level, where you also have to do arrangement of these. Like there is a basically saying there is a set of variables that represent masculinity, and then you have to take this one multiplied with this one for agency and this one with that one for agency and so on, because there's ordering also an issue. That is an issue. So you have to reorder these things, multiply them, and that gives you the outputs that you see in the network. Now you have to just do the reverse process, the inference,
Mhm.
which I'm guessing is possible because of all these bilinear models people have played with. You know, I played with some as well, and it's not that hard to
Mhm.
deal with them in an EM-like fashion, just iteratively fitting to both.
And if
sides.
it were fifth order instead of second order, do you
I don't
think
know,
it might
but
still have a chance?
Maybe there will be a chance. Be better than regression, I suppose. Just finding a regression, but maybe it would be interesting to see that. Has it been done, Lee, in word embeddings? Have they tried to figure out whether the embedding in RNN in the state of an RNN is hiding some high-level information by regressing to it in some way?
No, not that I know. But the earlier one that you're talking about, filtering out like Bill Freeman,
Yeah,
what you talk
right.
about, people have done that simply to to factorize different influencing factors,
Right.
and people have done that.
Yeah.
I mean, in speech people do that, like
Right. Just not on RNN state.
it's not. For DM, people try that. You get a speaker variation, environment
Yes.
variation. They're all separate from each other, just
Right.
like
Yeah, yeah.
image. You have
Yeah.
lighting,
Mhm.
information. And you can actually do that in the standard neural network
Yeah.
by simply controlling the learning schedules.
Oh.
We actually have done that as well. It turned out very. This is one of the major, Yasha Benjo called factorizing the disentanglement of the factors, in deep learning, and neural net is quite good at that, without actually having to do a lot of change in the architecture. Just you change the way you train the model, you actually can get that.
Yeah.
So that's
The language equivalent of that would be
so language.
trying to train it without tense. Like I could imagine like the
for language.
tense being kind of similar to lighting or
Yeah, so this is the general principle that in order for you, I mean that's one of the practical use of distributed representation. With distributed representation, you actually can isolate different factors that actually influence the final outcome. And if you local represent, you screw. You don't have that flexibility to do. So like the way in speech that people do is that in order to train particular layer, they only capture the phonetic differences and ignoring all the speaker differences. You actually can control the training schedule to make that happen. That's very similar to the one, and that's one of I think that when you read the literature talking about you distribute representation to disentangle the factors, and they make exactly that one.
Right, but they kind of have to know ahead of time what the factors are.
Yeah, of course. Yeah, but we know, right? Especially we know the noise.
Yeah.
It's a separate, more or less separate from
Yeah.
from
But
speaker
I think the
differences.
point of all of this is that the
And
brain
images as
somehow
well.
does that anyhow, and that's the representation it has. And the neural networks apparently work. You run an RNN on the text, and it generates something that seems to make sense. Well,
Yeah.
kind of makes
Well,
sense.
I mean, you're stating that, but.
Yeah.
Well,
Okay.
yeah, but maybe it's capturing, that will be the question. How much is it actually capturing? Is it capturing?
But you
the
know, I mean, that
events,
assumes that you
capturing
know
the
what are the factors that influence the final, like in the image is much easier, right? You know the lighting, you know. So what you can do is that you keep everything the same, changing the lighting environment. And you actually can isolate certain part of the
Right.
distribution, just
Right.
reflecting that change.
It's much harder. to
And
do
then the
that.
other one, you do another one. So actually, you can actually say that this part of the vector is doing this part of the vector is doing this, the other part is doing that. It's a very, very nice work.
Okay. But it's,
That has been done a
But
lot.
as Lucy was saying, it would be hard to do that in language, to insist that
Yeah,
you
that's
must
what-
make the
why-
story first and present,
Yeah.
present and then.
Yeah, I don't know how language is the equivalent for language. And the image is very clear, well, you know what they are. Now for language, maybe how different language, well, you know, okay, maybe, different language in English versus French express the same meaning of spin, for example. And then they have different expression. These are,
Can you take
Maybe equivalent.
can you take the English out of the input?
yeah, something like that. But if you know how to do that, you actually can extract some unilingual or higher level, then you can unify different languages. That's similar to image. You know,
We
those-
discussed the problem in the context of the response generation. I say
I see.
that different people have different
I
the
see.
language style.
Ah,
Right?
well, yeah.
The same meaning, but
Yeah.
Lucy.
But you have the same meaning, right? So they are all.
Just sort of play Lucy's vector with Chris' vector.
Mm-hmm.
We can say the same thing.
Yeah, so that could be, I mean, different language and also different dialect. That's
Yeah.
different, and then also different gender. And
Yeah.
there, these
But-
kind of factors are more or less independent of each other.
But I just
And then
don't
you
know
can
how
actually
to
model those.
train disentangle the vector representation.
Thank you very much. I think
Okay.
we should have arranged another lecture for alternative distributed representation. And for other people in the community, I think in that I talked to, the first time they read them all, they say that yours is the largest dimension. It's harder to deal with relative to others. I think you have arguments and the other one as well.
Right,
I think it'd be nice to.
right. I would like to accept your invitation to put my response on tape.
Okay. Oh, yeah, okay. Thank you very much, yeah. Okay, thank you.
Thank you.